then we'll come back to chapter 3 and talk about nomenclature next time, I think. Okay, so in this chapter, we're going to talk about a number of different topics. We'll talk about atomic mass. We'll also talk about Avogadro's number. We'll talk about moles. Um, we'll talk about empirical formulas, molecular formulas, what they are, how to solve for them. So a lot of stuff in this chapter here that we'll go through. Okay, so let us get going with it. So first off, one of the fundamental sort of properties of atoms is its mass, and we do talk about the atomic mass. The atomic mass is that number that we do see on the periodic table when we look at an element. So, for example, if we look over there on the periodic table underneath, say, oxygen, we'll see something like 16 uh, over there. That is the atomic mass. You know, you see something like carbon, 12.01. That is the atomic mass there of carbon. So remember, that's the top number there is the atomic number. Bottom number is the atomic mass. It is obviously related to the number of protons, electrons, and neutrons there are in an atom. But it does create sort of a problem for us because we can't really pick up an atom and kind of put it on a balance or a scale. Obviously, very, very sort of small in that sense. So a lot of times in chemistry, when we can't sort of directly measure something, what they will often do is pick something to use as sort of a standard. And they'll pick this thing and basically use it as a standard. They may assign it a particular value. They may measure its particular value that they're looking at, but they'll pick something to use really as a standard. And really for the atomic mass, they used an isotope of carbon to do that with. And they used what is known as the carbon 12 isotope. Carbon 12 isotope has a mass of exactly 12 AMU. So they chose this sort of isotope of carbon to use there for the standard. And they basically kind of compared everybody to it and said, hey, like this guy's only, 8% as big as a carbon 12 isotope. This guy maybe is a little bit bigger. This guy's a little bit sort of smaller than the carbon 12 isotope. And that's essentially how they sort of came about with all those numbers that we do see on the periodic table. So, for example, as we will probably see, they said hydrogen's about 8%, give or take a little bit more than that, of the mass that we see for a carbon 12 isotope. You take about 8% there of 12 and you get about a number like 1.008, which is what we see when we look underneath hydrogen there on the periodic table. So that carbon 12 isotope is by agreement basically sort of the standard that is used for our atomic mass. And that is also a unit that we could use when we do pull those numbers off the periodic table, like nitrogen is 1401. We could say that is 1401 AMU really in an atom is sort of the units that we would get there. So as atomic mass units per atom is 1401. We'll later see that that's pretty much equivalent to what is known as the molar mass in grams per mole, but we can use it as a sort of atomic mass units per atom. So sometimes atomic mass is basically referred to as atomic weight. And similar calculations, like the one I talked about there with hydrogen, were done to basically figure out sort of everybody's atomic mass. You can take 8.4%. Remember, when you convert a percent into a decimal, we're moving 2 places to the left, which is why the decimal is moved over. Times it by 12, again, gives you that number that we see on the periodic table underneath hydrogen. Similar calculations were done for things like oxygen and iron. And again, those are basically how we kind of get those numbers that are on the periodic table. One thing you might wonder, though, if we do, as I wrote up there a second ago for carbon, we do look at carbon, it does say 12.01. It doesn't say 12.00 like the carbon 12 isotope mass is. And there is a reason for this, and we're going to talk about that right now. The reason for this really is what we see on the periodic table and what we sort of use as the atomic mass on the periodic table is really an average atomic mass. Even though most people don't call it average, they just call it the atomic mass, but it's really an average atomic mass. And what is it sort of an average atomic mass of? It's an average atomic mass of all the naturally occurring isotopes for that particular element. So, most elements have multiple sort of naturally occurring isotopes that occur. And really what we see sort of on the periodic table is an average of all those naturally occurring isotopes sort of, I won't say added together, but sort of calculated in a sense. And that's because, for example, something like carbon has two isotopes. One is the carbon 12 isotope, and one is carbon 13 isotope. Carbon 12 isotope has an atomic mass of about 12, obviously. Carbon 13 isotope, much like the name implies there, has a mass of about 13 and some change. And when you sort of average those together, we get an average atomic mass for carbon of 12.01, which represents all the naturally occurring isotopes. How do you calculate the atomic mass? Well, you calculate the atomic mass by doing a sort of simple formula. You take the percentage of the first isotope times the atomic mass of the first isotope. And then what you do is you add it to the percentage times the atomic mass of the second isotope. And then you pretty much continue that pattern. If there's 3 isotopes, 4 isotopes, however many are. This percentage, as we'll see a little bit later as well in this chapter, this percentage is what's sometimes referred to as the relative abundance or percent abundance of an isotope. And obviously, if you have all the naturally occurring isotopes, when you add up the percentages, they should technically equal 100%, right? If you have all those naturally occurring isotopes that are occurring. So when we do something or look at something like carbon, again, if we have our sort of numbers here, we have the carbon 12 isotope that basically occurs about 98.89% of the time. We have the carbon 13 isotope that occurs about 1.11% of the time. And basically, we could do that calculation I just wrote out. And if we do that, that is what this calculation is here. That is our 98.89% converted into a decimal times the atomic mass of the carbon 12 isotope plus, and again, people always want to multiply here, but plus the percentage of our second isotope, which is the 1.11%, converted into a decimal, times the atomic mass of our second isotope there. And that is actually how we get to our 12.01 number that we see there on the periodic table, and 12.01 AMU. It is actually an average of all those naturally occurring isotopes that we have for a particular element. Any questions on that there? Now, it's important to note that, if you were able to sort of pick up a carbon atom, you would probably never find one that actually has this mass. You would either find one that has the mass of a carbon 12 isotope, or you would find one that has a mass of the carbon 13 isotope. So again, what we see on the periodic table is really an averaging of all the naturally occurring isotopes for a particular element. Again, most of the time people don't refer to it necessarily as average atomic mass, but that's essentially how we get to those numbers. Any questions on that there? When we do something like molar mass, we also, an atomic mass, again, typically when we take that number off the periodic table, 4 significant figures is sort of what we go to in terms of the numbers that we should take off or use. Now, atoms are very tiny, so obviously we avoid using very small numbers. The conversion, just so you know, in terms of into grams, is 1 atomic mass unit is 1.66 times 10 to the minus 24 grams. That's very small type number. And again, we use atomic mass units. Or later on, when we talk about molar mass, we use grams per mole. As we will see in just a second here, grams per mole and AMU per atom, essentially the same thing in terms of numbers. They've come out basically the same. Now, like I mentioned before, even though natural carbon does not contain a single atom with a mass of 12.01, we can treat it as though that is sort of the mass and that is sort of the atomic mass that we use for carbon, even though it's sort of an averaging of that. So if we were going to do sort of a conversion, again, we can kind of do that. 1 mass of a carbon atom is 12.01 AMU. And that is basically sort of the units that you can take off the periodic table. Again, if you look under carbon, it has that 12.01. And again, what that means is that there are 12.01 AMU really in a carbon atom. So if we want to know the mass of 431 atoms of carbon in this particular case in the units of AMU, that is what we would use for our conversion factor. Again, starting with our carbon atoms, using our atomic mass from the periodic table, atoms cancel, multiplying the 431 times the 1201 gets us 5,176 AMU would be the mass of 431 carbon atoms. Any questions on that there? Here's another one. Again, we could do it really for anybody on the periodic table. If we look at aluminum, if you look at the little box there, is 2698. So what that means is that there are 26.98 AMU in an atom. And again, we could use that as a conversion factor really either way. We could go atoms is a 26.98 AMU. And if we do sort of the same conversion here, our atoms are going to cancel, going to leave us with an atomic mass of 2024 in that particular case. Any questions on atomic mass here? A lot of times I will say, we don't necessarily, in a lot of calculations in chemistry, use the units of AMU a lot. We do use, as we'll see a little bit later on, grams per mole. So that's a very common sort of unit that we use for sure. How do we sort of measure percent abundances or relative abundance of isotopes and things of that nature? We could do something known as mass spec. And mass spec basically will allow us to get the masses and the relative abundance of different sort of isotopes by using this sort of machine. It sort of separates out everybody by sort of mass. And, depending on the mass, it will come out either first or later. And it sort of separates everybody out. We also get a certain sort of peak associated with each of the isotopes. And that will help us figure out sort of the percentages of those guys that are present. But basically, atoms and molecules are ionized, then kind of accelerated along a tube of a sort of magnetic field, and it sort of bends it. And then again, they sort of shoot out at sort of different times, if you will, based really on their size and mass as they're broken up into these sort of fragments. And we get a graph, something like this, for example. And again, we get our percent abundance here, somewhere in the 75-ish percent, a little bit of 25-ish percent, give or take a little bit. And, that gives us our relative abundance of each of these different isotopes. You could also see, again, separated by mass as they come out on sort of the graph as well. Again, giving you that different separation of these isotopes based on sort of their mass. When it means when atoms or molecules are ionized, they're kind of broken up into their parts, if you will. So they're kind of broken up into their kind of different isotopes. So ionized basically kind of means breaking apart something. And maybe this picture will help. So your sample kind of goes through here, and this is the part that kind of does that. They kind of heat it up a little bit, and as you heat it up, basically it kind of separates out everybody, kind of breaks apart everybody, which is basically what it means by being ionized. And as it goes through here, there's actually an electrical field, because when it does kind of break these guys apart, they sort of gain some charges, and we could take advantage of that sort of charges that gets made when it's ionized. So that's also what ionized means, breaking it apart, and also breaks apart into ions, right? So it has things with charges. And again, taking advantage of those kind of opposites attract and same guys are repulsed, that allows them to go through this electrical field. And magnetic field also works sort of the same way. I remember, I think we talked about it when we were talking about Rutherford and different beams, right? If you have like a electrical field and you shoot something that bends towards the positive guy, then that's probably more of a negative. If you got something that's positive, it will bend towards the negative side. You have something with no charge, it will just kind of go right through the middle, right? And that's sort of the idea here. And what ends up happening, as you can kind of see, lightest particles sort of end up over on this side of the detector, which obviously would relate to a spectrum that we would see, and heavier guys end up on this side. And depending on sort of the amount that's there, will give us sort of different peaks in terms of the percentages that are present as it comes out. So ionizing it, really kind of breaking it apart into little pieces that do have charges, and again allows it to basically be manipulated as it goes through this mass spec to sort of give us that separation that occurs. Any questions on that there? Okay. So why don't we try one here to calculate the atomic mass? So why don't you give it a go? And again, you want to use that formula we talked about, that the atomic mass is the percentage of the first isotope times the atomic mass of the first isotope plus the percentage of the second isotope times the atomic mass of the second isotope, and so forth. So take a moment here and figure out what you get here in terms of our atomic mass for these two isotopes of copper. And you're going to use those to figure out what is the atomic mass of copper. So take a moment or two and see what you come up with here. It's the one that we saw earlier, where we're calculating the atomic mass, and basically the atomic mass is the percentage of the first isotope times the atomic mass of that first isotope plus, and again, that's an important part. Very often, like I said earlier, people like to multiply at that point, the percentage times the atomic mass of the second isotope. And again, if you had more than that, you would sort of continue that pattern. So if we sort of look at the information that's given to us here in the problem, we do have, let's see here, we have copper 63 that has a percentage of 69.17% and an atomic mass of 62.9396 AMU. We have copper 65, which they do not give us the percentage, but they do tell us it is 64.9278 AMU. So going under the assumption that these two isotopes are all the naturally occurring isotopes for copper, and again, we can probably safely make that assumption here in this problem, since those are only two given to us. We could assume that if we had all of them there, we should have a grand total of 100%. We already know that we have 69.17% is the copper 63, that means that the other isotope should have a percentage of about 30.83 in this particular example percent. So the first thing we probably want to figure out is the percentage of that missing isotope. And again, you could assume probably 100% in this particular example. Now we pretty much have everything that we need to calculate the atomic mass. So the atomic mass here would be our first percentage. And again, you could divide it by 100 if you want. I'm going to just move the decimal point. So that's going to give me 0.6917, which is this guy converted into a decimal, times 62.9396 AMU. Then I'm going to add it to my second isotope, which I just calculated. And again, I'm going to just move the decimal to 0.383. We're going to times it by the atomic mass of that isotope, which was given to us. And if we do all that good stuff there, looks like we get 6355 AMU. And if you look on the periodic table underneath copper, you will actually see that number there, 65, basically 6355 as well. Question on that calculation. So basically percentage, which again is sometimes referred to as the percentage, sometimes referred to as the percent abundance, sometimes referred to as the relative abundance of these different isotopes. But basically the percentage times the atomic mass of each individual isotope, and then you add them all together. That gives you really the average atomic mass and sort of the number that we see on the periodic table, which means if you were doing this problem sort of backwards and weren't given the atomic mass but had to find the mass of an isotope or something like that, you could use the number on the periodic table as your average atomic mass. Any questions on that calculation there? Okay. So the next thing we're going to talk about then is moles and Avogadro's number. So in life, we have a lot of sort of numbers, or not really numbers. We have a lot of words that really do represent some amount of something. So like it shows there, if you have a dozen of something, that means that you have 12. If you got a pair of something, that usually means you have 2. Hey, if you got a gross of something, 144, just in case. Good Jeopardy question. So if you have a gross of something, that's 144. And in chemistry, we do also have a name that basically represents a certain amount of something, and that is the mole. Not the furry guy, but we got the mole here. And that is actually the abbreviation for mole is this guy right here. It is MOL. They had it abbreviated somehow, so they took the E off. I will say sometimes people get confused on that abbreviation because when they see it, they automatically sometimes think of molecules. So if you see MOL, it most likely is representing moles here in chemistry. And what does a mole sort of represent? Well, just like a dozen represents 12, a pair represents 2. If you have a mole of something, it actually represents, as it shows on the bottom there, 1 mole is 6.022 times 10 to the 23. That is what is sometimes referred to as Avogadro's number. Now, the interesting about Avogadro's number is the units associated with it. It really can be pretty much any unit you like. It could be particles if you're kind of dealing with those things. You could use atoms if you're dealing with atoms. You could use molecules if you're dealing with molecules. You could do pizzas if you're having dinner. You could use shoes in case you need to walk to get your pizza. But probably here in chemistry, we will use most of the time, obviously, these 2 units, which are atoms and molecules. So what do we kind of use Avogadro's number for? Well, we use Avogadro's number really as a conversion factor. And it is a conversion factor that allows us to go from moles to atoms or molecules, or backwards. If you're starting with atoms or molecules, you could get yourself to moles. Again, if you're starting with moles and wants atoms or molecules, you are basically going to multiply by Avogadro's number. Again, you want to make sure you do use your exponent button here. Moles will cancel, leaves you with atoms, or it could be molecules if you're dealing with that. Or if you're starting with atoms or molecules, you would actually divide by Avogadro's number. So you would put it on the bottom. Again, the atoms would cancel, and that would leave you with moles. So we use Avogadro's number really as a conversion factor, and you can do it for anything. And what I mean by that is if you had 1 mole of hydrogen, that would contain 6.022 times 10 to the 23 atoms of hydrogen. If you had 1 mole of nitrogen, that would also equal 6.022 times 10 to the 23 atoms of nitrogen. If you had 1 mole of water, that would be 6.022 times 10 to the 23. But because water is not an atom, we would use molecules here of water, basically. So when you say really you have 1 mole of something, it is representing that 6.022 times 10 to the 23 number. And you could use atoms, you could use as molecules. Should you use Avogadro's number in every calculation you ever do? The answer is no. And sometimes people try to do that because they're like, I learned this number, I probably should use it somewhere. And they ended up, sort of using it in the wrong place or not correctly. You should only really kind of whip out Avogadro's number and use it in a calculation if you are given a number in the problem that deals with atoms, molecules, particles, or you're asked to solve for something in one of those units, atoms, molecules, or particles. If there's no mention of any of those things, you really shouldn't be using Avogadro's number. So sometimes, again, people like to use it maybe in too many places along the way. So as mentioned here, again, really another common sort of conversion that we use a lot is molar mass. So what is molar mass? Well, molar mass is the mass there are in 1 mole of anything. And molar mass we can actually get from the periodic table as well. It is really the same number that we were just talking about in terms of atomic mass. So molar mass means if I went to carbon that there are 12.01 grams of carbon in every 1 mole of carbon. That gives us basically 12.01 grams per mole as our molar mass. You can use it as a conversion factor. You could flip it around, put the moles on top, the grams on the bottom for carbon. You could do it from anybody on the periodic table. The molar mass of sulfur, right? If you looked at sulfur, it says 3207. That means in 1 mole of sulfur, there are 32.07 grams of sulfur. Molar mass of sulfur would be 3207 grams per mole. Or again, you could use it alternatively as a conversion factor as well. What about something that's not one sort of element by itself, like water, for example? We could also calculate the molar mass of water by simply adding up all the parts. There are 2 hydrogens, each would be 1.008 grams per mole from the periodic table. There's 1 oxygen at 16 grams per mole. That would give us a molar mass for water of 18.02 grams per mole. Again, you could use it as a conversion factor as well. If you did something like CH4, you would do the same thing. There's 1 carbon at 12.01 grams per mole on the periodic table, plus 4 times the mass of, not oxygen, but hydrogen would be good if I Put the right number there. 1.008. There we go. 1.008 grams per mole. And again, if we sort of add this together, we get about 16 there, basically. 1604 grams per mole. So molar mass comes from the periodic table. A couple of things that I pointed out, and just to make sure, molar mass is essentially the same as the AMU atomic mass per atom that we were just talking about. And it's really because it is, kind of Avogadro's number that ties it together, and it ends up being numerically the same. What is molar mass used for? Well, molar mass is used for a very important couple of conversions here in chemistry, and that is going from grams to moles and backwards, moles back to grams. So if you have grams and you want moles, you would divide by the molar mass from the periodic table. The grams would cancel. You would end up with moles. If you started with moles and you want grams, you would multiply by the molar mass on the periodic table, and that would get you grams. Any questions on molar mass? Now, I think we'll see it maybe in here as well. We could get the molar mass of, say, something like sodium chloride, which would be sodium is 2298, I think, grams per mole, or 99. Plus our chlorine, which is 3545 grams per mole. That will get you something like 5844 grams per mole. What did it say? 58.44. There it is. 58.44 grams per mole. Now, probably most of the time people will refer to this as molar mass. I'll refer to it probably as molar mass, and a lot of times people will do that. But sometimes people may not refer to it as molar mass, and the reason they won't refer to it as molar mass is because this guy is a ionic compound. And sometimes, some people will use some different sort of names for things that are ionic. So sometimes people will not necessarily call this molar mass, because molar mass sort of implies that the substance is sharing electrons and all that kind of stuff. Sometimes people call this the formula mass. And that's sometimes a term that's used for ionic compounds when you calculate really the molar mass. I personally will just use molar mass for everybody. And a lot of people will as well. But you'll sometimes see, sometimes people will kind of use that formula unit. And that's really because an ionic bond or ionic compound is not sharing electrons. They're held together by positive negative attraction, like we talked about. And they sometimes are referred to as formula units in that sense, positive, negative guys sort of together. And that's why sometimes people will refer to it as a formula mass as well. Is it a molar mass? But I personally will probably use molar mass. How all these guys tie together? Well, there are, as it shows there, 12.01 grams of carbon in 1 mole of carbon. And in 1 mole of carbon, there would be 6.022 times 10 to the 23 atoms of carbon. Same thing here in water. There would be 18.02 grams of water in every 1 mole of water. And in 1 mole water, there would be 6.022 times 10 to the 23 molecules of water as well. So again, that is sort of the tie-in between sort of molar mass and Avogadro's number. Any questions on that there? Each of these things do represent 1 mole of a substance, and you may look at this, or you may look at another sort of picture or something like that and look at it and go, it doesn't look like the same amount. Even though it all says it's 1 mole of a substance, these all don't look like maybe the same amount or quantity of it, sort of what's going on. And if you just think about sort of the numbers that we see on the periodic table, for example, if we look at sulfur, it's 3207. And that basically means there's about 32.07 grams of sulfur in 1 mole. But, if you had something like carbon, carbon is only 12.01 grams per mole. And again, 1 mole of carbon represents, in terms of sort of a physical quantity of carbon, about 12 grams, while 1 mole of sulfur represents sort of a physical quantity of about 32 grams. So that's why very common picture sometimes in these chapters is maybe not something like this, but they'll put in a beaker 1 mole of things and it'll look like, wait, there's different amounts. And again, the reason why there's different amounts is because of that. A mole of something, doesn't equal the same amount in terms of grams. What is that relationship again between sort of AMU and grams and all that? That is that's sort of what we see here, that relationship between sort of AMU and grams. And again, that's sort of the conversion. And that's really why, when you look at something, as like the atomic mass in AMU per atom, and you kind of convert it into kind of grams per mole, it comes out really the same. And by using these sort of conversions here, you sort of see that, if you took 12.01 AMU per atom and you did a little conversion where you took 1 AMU is the 1.66 times 10 to the minus 24 grams, and then you did your sort of atom, there's 6.022 times 10 to the 23 atoms per mole, and kind of use Avogadro's number. It all sort of works out the same when you kind of do it numerically there. If you do this whole kind of conversion, let's see here, atoms cancel, AMU cancels, leaves us grams per mole, and surprisingly, you end up back at 12.01 grams per mole. So numerically speaking, using the conversions between AMU and grams and Avogadro's number in moles, it gets you to the same number. So that's why we say that the AMU per atom in terms of the atomic mass is the same as the molar mass numerically, because it actually does work out that way. So here's just a little sort of decision tree here of like we talked about. Again, our molar mass is really what we want to use to go from grams to moles and backwards, while our Avogadro's number, we want to use that to go from moles to atoms or molecules and back. So those are the things you want to watch out for as you're using these numbers. Obviously, you want to make sure you use your exponent button as well. So once you give this one a go, calculate the number of grams there are in 15.7 moles of iron. Iron on the periodic table looks something like this. And 55, 85, I think. Getting old. And while you're at it, why don't we do how many grams there are in 327 moles of C2H4, and see what you come up with that. I'll put those guys up there as well. Carbon 12.01 and hydrogen 1.008. All right, so take a moment or two and kind of calculate both of those, see what you come up with. They're in 15.7 moles. First off, I'm going to know that I am not going to use Avogadro's number here because there's no mention of really atoms or molecules or anything like that. So really, I just need to go from grams, or moles to grams. And again, that is the molar mass from the periodic table that's going to do that. Iron would be 55.85 grams per mole. Again, typically when we take that number off the periodic table 4 significant figures is sort of what we go with. So we're just going to really do it like a conversion problem. So I start with my 15.7 moles of iron. I want to get rid of iron. So basically I want the moles to go on the bottom, the 85 grams up on top. The moles will cancel. We're basically going to take 15.7 times 55.85. That's going to give us something in the ballpark of 876.8 grams of iron. In terms of significant figures, probably based off of this number, which is 3, probably taking that now to 877 grams of iron. Any questions on that calculation there? Now, looking at the one I just made up there, we're also here looking for grams. We have moles, but here again, we don't have one thing. We have really a molecular formula here. We are going to use the molar mass because again, there's no mention of atoms or molecules. Remember, MOL is not molecules, but moles. But we do just need to add up the parts here. So for something like C2H4, if I want the molar mass, we're just going to go to the periodic table. And like I said, pretty much add up all the parts. So each carbon is 12.01. There's 2 of them. There's 4 hydrogens at 1.008 grams per mole. We're going to multiply those guys and add them together. That gets us something like 2805 grams per mole. Again, really, we're going to use molar mass as our conversion factor. So we'll start with the 327 moles that was given to us in the problem. Same sort of approach. Moles are on top, so we want moles on the bottom so they cancel. The 2805 grams there. Moles cancel, going to get us 327 times 28.05. And that gets us a 9172.35 grams of C2H4. Same thing on the sig figs, probably going back to that number. Gonna take us to right there. And that would end up probably being 9170, no decimal point, grams of C2H4. Any questions on that calculation there? Okay. All right. So let's take a look here. We got, why don't you do these couple here examples you have coming up. Let's do how many moles of lithium. Let's also do how many atoms are there in 0.551 grams of potassium. So give that a go. Lithium, 6.941. Potassium, 19, I believe, unless they've changed. Maybe they have. 3910, they did. 3910, they didn't. I just said the wrong number. So give those 2 a go, see what you come up with here. Okay, let's take a look at this one here and see how we're doing. There it is. So first one, we know how many moles of lithium are there in grams. So again, no mention of atoms or molecules or anything like that. So again, it's a grams to moles conversion. That means we just pretty much need to go to the periodic table, in this case for lithium. And again, that number means that there are 6.941 grams per mole would be the molar mass for lithium. That we will again pretty much use as a conversion factor here. In this case, we actually want to get rid of grams. So we're going to put the grams on the bottom. The number always stays with the grams, and it's always 1 mole when you do molar mass. So the moles part should always be 1, and the number should always stay with the grams part when you calculate the molar mass. That means we're essentially dividing 77.8 by 6.941. That's going to give us 11.2 moles of lithium in this case. Any questions on that one there? All right, taking a look at the next one, which is, I think, your next example. How many atoms are there in 0.551 grams? So atoms is a key word here. Atoms means we do need to use Avogadro's number here, and that is 1 mole is 6.022 times 10 to the 23 atoms. In order to use that, we need things in moles, and they're not in moles, which means we also need to use the molar mass here in grams per mole. So we need to go using the molar mass to convert our grams to moles. We then can use Avogadro's number to go from moles to atoms. So again, we would go to the periodic table, and that means that there are 39.10 grams per mole would be the molar mass of our potassium. That is where we'll start because the units they gave us are grams. We're going to get rid of the grams, so we're going to divide by the 3910 grams per mole here of potassium. Grams cancel. You could get an answer at this point if you wanted to. That answer would be in moles. And if you did get an answer at this point, and you absolutely don't need to get an answer at this point, but if you did, you'd be somewhere in the ballpark of 0.01409. Again, I'm not going to round very much at this point. In fact, I'm not even going to round the number on my calculator. I'm just going to continue on with that number. And now we can use Avogadro's number here to go from moles to atoms. We're going to multiply by Avogadro's number, making sure that we do use our exponent button here. So we're going to times that by 6.022, exponent button 23. And that is going to get us 8.49 times 10 to the 21 atoms of potassium here in 0.551 grams. Question on those steps. Obviously, you don't need to get an answer in between. You could just continue on with the calculation if you wanted to. I would highly recommend that you do set these up as conversion type factors, dimensional analysis. Very, very common. People screw up. They multiply when they should divide or divide when they should multiply. Any questions on either of those two? Okay. That one we just did. I'm going to kind of skip these here. So we kind of just did similar ones, but I do want to talk about this particular one here and kind of do it here with you. In this particular one, we're interested in how many hydrogen atoms there are in 72.5 grams of C3H8O. In this particular case, we're not interested in the entire thing here. We're interested in just the hydrogen atoms and not the whole thing. So we can basically use the formula as a conversion factor. And we could say in 1 mole of the entire thing, these numbers that we see on the bottom, these subscripts, and 1 for that guy at the end, these guys represent how many moles there are of each of these guys. So we could almost do a sort of a mole to mole relationship for 1 mole of the whole thing. It gives us 3 moles of carbon. For 1 mole of the whole thing, it gives us 8 moles of just hydrogen. And for 1 mole of the whole thing, it gives us 1 mole of oxygen. So if we're not interested in the whole thing, which is sometimes a very common question, we can actually use the chemical formula as kind of a conversion factor, using those numbers or subscripts on the bottom as how many moles there are of each of those particular elements. Any questions on that? Now, since this relationship here is a mole to mole relationship, this number here, in order for things to work out, does need to be in moles as well. So the first thing we need to do really is take those grams of the whole thing to moles. We need to go from moles of the whole thing to moles of just hydrogen. And then we need to go from moles of hydrogen to atoms of hydrogen. So that's sort of the game plan here. So we'll start with the molar mass of that so we could get to the grams of the whole thing. So in this particular case, we have 3 carbons at 12.01 grams per mole. We also have 8 hydrogens at 1.008 grams per mole. We also have 1 oxygen at 16 grams per mole. So if we add all that up there, we will end up with 3 times 12.01 plus 8 times 1.008 plus 16 gets us 6009 grams per mole. And that is the molar mass of the entire guy, the C3H8O. So we're going to use that at the beginning step here. We're going to go 72.5 grams of the entire thing. Using our molar mass of the entire thing gives us 69.09 grams on the bottom and moles of the entire thing. That will cancel out the grams. At this point, if I stop the calculation, I'm in moles of the entire thing, which is not necessarily what I want because ultimately I want to get to just hydrogen. So this is again where the formula comes into play. We could use that sort of mole to mole relationship between the whole thing and just hydrogen. And again, you could get an answer or you could continue on. So what we see is for every 1 mole of the entire formula, we end up with 8 moles of just hydrogen. And using that formula right here, that's going to allow us to go from the whole thing to just the hydrogen part. The moles of the whole thing will cancel. Any questions on that so far? Now, are we done? We're not, because if we stopped right at this point, we're close to what we want. We're in moles of hydrogen. We got one more step to go. And again, to get us to atoms, that's where we're going to use Avogadro's number. So we will do that as our last step. We're going to multiply by Avogadro's number here. The moles will cancel and leave us with Avogadro's number. And thank you. I think you're correct. It is 60. I have it on my calculator. I think I might have said it right, but I think I read it wrong. Thank you very much. It is 60.09. Thank you. So that will cancel out our moles. So now that we got the right molar mass there, we're going to multiply everything on top. So that's 72.5 times 8 times 6.022 to the 23. We're going to divide it by the molar mass, which is 60.09. And not hit the wrong button there. Try that again, 60.09. And it looks like that we end up with 5.81 times 10 to the 24 atoms of hydrogen. Any questions on that one there? Now, this is sometimes a very common sort of question. Sometimes they're not interested, again, like I said, in the whole thing, but they're just kind of interested in sort of one part of it. And again, you could use the actual formula as a conversion factor. Questions on that? Okay. So why don't you try this one here? There's 2 questions. Basically, there's 2 parts of the same question. We want to know how many moles there are and how many molecules there are of ethanol here. And again, carbon 12.01, hydrogen 1.008, and oxygen 16 from the periodic table. All right, take a moment or two and see what you come up with. 2 times 12.01 grams per mole plus 6 times 1.008 grams per mole for the hydrogens and a 16 grams per mole. All right, let's see here. It looks like 4607 grams per mole. So that would be really the first part here. We would use our molar mass again as a conversion factor. We're going to divide by 46.07 grams per mole. grams are going to cancel, and that's going to get us 23.2 divided by 4607, going to give us 0.504 moles of C2H6O. Any questions on that part of the calculation? At this point, we now have it in moles, so we can use our Avogadro's relationship that 1 mole is equal to 6.022 times 10 to the 23 molecules in this case. So continuing on with our calculation here. We are going to actually multiply here by Avogadro's number. And again, we would use molecules here as the unit because we're dealing with that per mole. Moles are going to cancel, and that will get us something in the ballpark of 3.03 times 10 to the 23rd molecules of C2H6O. I personally didn't round my number on my calculator, so if you did round and use that number, you might get 3.04 times 10 to 23. It's okay. Any questions on any of those steps, or how to go from grams to moles, moles to grams, Avogadro's number? Any questions on any of that there? Okay. So obviously grams to moles, moles to grams, and all that stuff is a really important aspect of obviously chemistry and what we use a lot for. So let us then talk about, or skip this one, it's kind of similar to ones we did before. Let's talk about another sort of aspect of mass and stuff, and that is what's sometimes referred to as the percent composition by mass. So you basically can figure out the percent composition by mass of each element in a formula by basically getting the molar mass of the entire molecule or compound, and we divide basically each of the parts by it. So if we were looking at this guy here, which is the guy we just did, as an example, and we want to figure out the percentages by mass of carbon, hydrogen, and oxygen in there, we would first get the molar mass like we just did. And to find the percentage of carbon that is present, we can see from the formula that there's really 2 moles of carbon present. So 2 times the mass of carbon from the periodic table divided by the mass of the entire compound times 100%. And that would get us a percentage by mass of carbon in this particular guy as, call it 52.14%. So basically, by mass, about 52% of this compound is made up of carbon. We could do the same thing for hydrogen. There's 6 of them in the formula. So 6 times 1.008 grams per mole from the periodic table divided by the molar mass of the entire compound times 100%. That gets us 6 times 1.008 divided by 46. Whoops. Come here. 0.07. There you go. Times 100. About 1313 looks like. So it is made up of about 13% hydrogen by mass. At this point, we could do the same thing for oxygen. There's only 1 oxygen present. Divided by 46.07 grams per mole times 100%. And that would get us 16 divided by 46.07 times 100%. And we see that oxygen makes up about 34.73% of this molecule. By the way, because oxygen was the last element present, you could have added those 2 together and then subtracted by 100%, right? And that would get you your 34% as well. So, there's a couple different ways you could kind of do that. Question on how to calculate percent composition by mass. Yeah, we're actually leading right into that. So the question is, can we use these to help us find the sort of formula of a compound? That's actually the next slide. So hopefully this will answer that question for you. So this is a very common approach that's used in the laboratories to help us find a certain type of formula for a particular compound, maybe even an unknown compound. And that is what is referred to as the empirical formula. And the empirical formula, before we get started on the problem, the empirical formula is the simplest whole number ratio of what's present. So the empirical formula does not necessarily tell you 100% of the time, like exactly how much of each element is present, but it does give you really the simplest whole number ratio of what's present in that particular compound. And that's different than the molecular formula. The molecular formula tells you exactly how many atoms of the elements are present. So, for example, if we had H2O2, which is hydrogen peroxide, that is two hydrogens for every two oxygen relationship. That would simply reduce down really to one hydrogen and one oxygen. The empirical formula for H2O2 would be HO, which is obviously a 1-to-1 relationship. Same thing if you have like C2H4, if that's the molecular formula, that's basically two carbons for every four hydrogens. That's the same as one carbon for every two hydrogens, which means the empirical formula for that guy would be something like CH2. So the molecular formula tells us exactly what's present in terms of the elements. The empirical formula doesn't necessarily tell us that. It gives us the simplest whole number ratio of what's present. Now, when we calculate the empirical formula, sometimes it is the same as the molecular formula. If we have two hydrogens for every one oxygen in water, that is as simplest as you could get. You can't really reduce it down any more than that. So water, H2O, would be both the molecular formula and the empirical formula. So sometimes they're the same. So to actually calculate the empirical formula, you want to first get the mass percent, which is sometimes given to you. And if we're given the mass percent, a very good way to convert those to grams is to assume that you have 100 grams. If you assume you have a 100 grams, then basically the percentages are the number of grams. What that means is if you have 100 grams and you have 24% potassium, then you have 24 grams of potassium, right? So it's a good way to keep everything the same. You then want to go from grams to moles of each element. You then want to divide by the smallest number of moles. So for example, let's say we had 2 moles of A and 4 moles of B in a made up example. We would then want to go and divide everybody by 2, as that's the smallest number of moles. When I do that for A, that gives me 1. When I do that for B, that gives me 2 in my made up example. And if we hit all whole numbers, that would be our empirical formula, would be in my made up example here, A, B2. Now, if you do not hit whole numbers, let's say, for example, we had 2 moles of A and 5 moles of B. Here we would divide by 2. But when we do that, we end up with 1 for A, but we end up with 2.5 for B, which would mean our empirical formula would be A, B, 2.5. Can't have like a half a mole of an element. So what we need to do in that case is figure out a number that we can multiply 2.5 by to get a whole number. So if I take 2.5 times 1, that is 2.5. Take 2.5 times 2, that is 5, I believe. That means I should multiply this entire thing by 2. Not just the B, but the A as well. And that would give me A2, B5, all whole numbers, And that would be the correct empirical formula. So sometimes you're not lucky and you don't hit perfect whole numbers. So sometimes you do have to kind of go and figure out sort of a conversion factor to do that. So let's take a look at this one and see how we go through these steps here. So let's kind of line it up. First off, we have potassium, manganese, and oxygen. We have the percentages given to us. So we might want to first just quickly add up all those percentages. And if we do that, we end up with 2475 plus 3477 plus 40.51. That's approximately 100.03%. That's essentially 100%. What that tells us is we're not missing anything, right? So we want to really convert these percentages into grams. So we could assume that we have 100 grams of this substance. And what that means is for potassium, I would then have 24.75 grams of potassium. For Mn, I would have 34.77 grams. And for oxygen, I would have 40.51 grams. Again, all I did was assume that I had 100 grams. It keeps the numbers the same. It's the simplest way to do that. Now that I have them in grams, really the next thing I want to do is convert these guys into moles. So to convert them into moles, what I'm going to do is go to the periodic table. I'm going to use the molar mass of each of these guys. So potassium from the periodic table is 3910. Mn from the periodic table is something. I think that's 5494, I think. I'm getting old. I don't think I can see that far anymore. 5494, give or take. Hopefully not too much taking. And oxygen is 16. We'll see in a second if I guessed right there. Mm-hmm. So we're just going to convert all these guys into moles. And if we do that for our potassium, we end up with 0.63299. I'll just take it a little bit far. For our Mn, we end up with 0.63287. And for oxygen, we end up with 2.5319, we'll call it. Any questions up to that point? Now that I have converted everybody into moles, basically what I want to do now is find the smallest number of moles. In this case, we have a couple that are pretty close, but it does look like the Mn is the smallest. So what I'm going to do is take each of those things. So potassium would be 0.63299 divided by 0.63287. Mn would be 0.63287 divided by 0.63287. And oxygen would be 2.5319 divided by 0.63287. Again, that number comes from here. That looks like the smallest number of moles. So if we do those divisions, essentially here we get 1. Essentially here we get 1. And on the bottom, we don't get 1, I hope. But we do get about 4. Any questions up to that point? So now that we've divided by the smallest, that gives us really the moles of each of those guys. And since they are all whole numbers in this case, we have just made our empirical formula. It would be KMnO4, which is potassium permanganate. So this is the step to calculate the empirical formula. We want to get the number of grams of each of the elements. We want to convert those grams into moles. We want to find the smallest number of moles and divide everybody by it. At that point, like we did in this example here, if we do hit a whole number on everybody, that is good. That would be your empirical formula. Again, if you don't hit a whole number, you need to do some type of sort of way to figure out a factor to multiply it by to get everybody into a whole number. When can you round? You should only round in a textbook problem or, this type of problems if you're really, really close to a whole number. So maybe you're at like 3.999 or 3.998 or something like that, or maybe you're at 4.01. You pretty much should round at that point. If you hit a number when you're doing the division part, so like when you're doing this part here, for example, and maybe you hit a number like, we'll go back, maybe hit a number like 1.33 or with like a 0.33 or a 0.50, or something like that. These numbers are too far to round. So these are common numbers where you need to kind of use a factor to get you out of it. But again, if you ended up with like 1.997, that's probably pretty close enough to 2 to round. Or maybe you ended up with like 3.01 or something like that. That's pretty close to 3. But, if you ended up with like 2.50, too far to round in that situation. Question on that. The importance of an empirical formula is oftentimes there's sort of the first formulas that are sort of discovered by perhaps a researcher or something like that. And the importance of it is it gives you really the basic combination that's happening between, say, the different elements, the basic ratios at which they are coming together in this particular compound. Like, for example, hydrogen peroxide. The basic way that hydrogen peroxide is coming in, even though the correct molecular form is H2O2, is it's coming together in a basically multiple of a 1 hydrogen to 1 oxygen relationship, while something like the C2H4 that we saw earlier on the left there, when it is coming together, it is basically always coming together in basically a 1 carbon to 2 hydrogen ratio in its sort of simplest forms. So empirical formulas oftentimes in the laboratory are the ones we might try to discover or sort of find, because what we can do is very simple sort of procedure like the experiment we're going to do today, to figure out really sort of the simplest ratio of what's present of each of those things. And then that allows you to understand how things come together. So if you remember, back when we talk about Dalton and all those guys, they had all those sort of laws of definite proportions and things like that. And these allow us to understand the basic sort of way that, things do combine and come together, in a particular compound. Other questions on that? Okay. All right, so we'll stop there here for now for lecture, and we will then, since we just talked about empirical formulas, we will talk about experiment 7 today. A reminder that we are having a quiz, I believe, right, on Thursday. So we'll have a quiz on Thursday at the start of lab, and it will be all about, I believe, bonding, if that's for you guys. I think bonding. I think my other one is about naming, but you guys are bonding. So we'll do that after lecture. She'll have lecture like normal. And then we will, take a break and then go to the lab. And at the beginning of the lab, we'll take the quiz like we've kind of taken everything else before, camera on, and then obviously proper view. We will take it, and then afterwards we'll maybe take a little break and then talk about what was on tap there for lab on Thursday, which I think might be a study assignment on